Hello students, my name is Lalit Chauhan and I am chemistry lecturer. Today I'll be teaching you chemical kinetics, and this is a very important topic. Every year they ask at least one question from chemical kinetics. It is very easy topic also, so let's begin that. Physical chemistry can be broadly divided into two subheadings: thermodynamics and chemical kinetics. Thermodynamics tells you how far a reaction will go or whether a reaction will occur or not, while chemical kinetics tells you if a reaction will occur, how fast it will occur. So in short, chemical kinetics is all about finding the speed of reaction, or you can say finding the rate of reaction. How we will proceed into that? So for the convenience, we have divided chemical kinetics into these 7 subtopics. They are rate of reaction, factors affecting rate of reaction, rate law, order and molecularity, collision theory and Arrhenius concept, zero order reaction and first order reaction. We will try to complete at least 3 to 4 subtopics today, and rest we will do in the coming lectures. So let's begin with rate of reaction. Okay. So students, let's come to the questions. While doing the questions on rate of reaction, just keep in mind that try to connect all the rates of appearance and disappearance via rate of reaction. See, for example, in this question, they have given you rate of disappearance of hydrogen. They have given this value. So what is rate of disappearance of hydrogen? It is nothing but minus of dH2 by dt. And what they are asking, rate of appearance of ammonia. What is that? That is dNH3, change in concentration of ammonia upon time taken. Now I know that rate of reaction will be equal to minus of dN2 by dt will be equal to minus of dH2 by 3 dt. Remember to divide by the stoichiometric coefficient to get rate of reaction, which should be equal to dNH3, change in concentration of ammonia, divided by time taken and the stoichiometric coefficient, that is 2. Since they have given this data and they are asking the data of ammonia, so I should be concerning myself with this part only. Now this minus of dH2 by dt is given, so this section is given. So put the value there, that will be 3 into 10 to power of minus 3 upon 3 should be equal to, they are asking this thing, rate of appearance of ammonia. So this part will be cancelled, bring 2 over here, so I will get what? dNH3 upon dt will be equal to 2 into 10 to power of minus 3 moles per liter per second. So this is the rate of appearance of ammonia. What I have done, basically I have tried to connect all the rate of disappearance and appearance with rate of reaction. Okay, I hope this is clear. So let's come to the next question, students. Here they have given a reaction and they have also given you the rates of disappearance of reactant and rate of appearance of products as well, and they are asking you the relationship between K1, K2 and K3, K1, K2 and K3. Now whatever they give in the questions of rate of reaction, please try to connect all the rate of appearance and disappearance via rate of reaction. So I'll begin with the solution. Rate of reaction will be equal to, in terms of rates of disappearance, this will be minus of dN2O5 divided by dt, and the stoichiometric coefficient is 1, so there is no problem. This should be equal to dNO2 divided by the stoichiometric coefficient is 2 dt, which should also be equal to what? dO2, the rate of appearance of O2 dt, and divided by the stoichiometric coefficient, which happens to be what? 1 by 2, so 2 will go up. This will be the case. Now replace these values. So this will be actually K1 N2O5 should be equal to, this value is given as K2 N2O5, K2 N2O5 divided by 2 should be equal to, this value is given as K3, this value is given as K3 into N2O5 and into 2, the stoichiometric coefficient. Now once they are equated, the concentration of N2O5 can be cancelled and we are left with K1 equals to K2 by 2 equals to 2K3. Simplifying that, on multiplying by 2, I will get 2K1 equals to K2 equals to 4K3. Now this is a very famous question. Many a times NEET and other entrance examinations have asked this question. So in order to do these questions, remember that connect all the rates of disappearance and appearance via rate of reaction. Okay. This next question is very interesting question with a catch, and I have found many people going wrong with this question. Let's see this question. They have given the equation and they have also given you if rate of appearance of SO3 is 8 into 10 to power of minus 3 grams per minute. This grams per minute is the catch out here. What happens normally, the data given is in moles per liter per second or per minute, but here they have given data in grams. Remember that, students, this equation is written in moles, the data given is in grams, so there is a mismatch. So to remove that mismatch, I should convert this grams into moles. So what I should do to convert this grams into moles, what I should do, I should divide this grams by the molecular weight of SO3. So that will be now 8 into 10 to power of minus 3 divided by the molecular weight of SO3, that will be 80. That will give me, that will be 10 to power of minus 4 moles per minute. Now this 10 to power of minus 4 moles per minute is what? Now this is the rate of appearance of SO3 in moles per minute. Now I know that the rate of reaction can be written as minus of dSO2 by 2 dt should be equal to minus of dO2 by dt should be equal to dSO3 by the stoichiometric coefficient is 2. This will be this thing. Now this part is not useful for us because they have given this data and they are asking this data. So this can be written as minus of dSO2 by 2 dt will be equal to dSO3 by 2 dt. This 2 and 2 cancels out. This is now what? This is rate of appearance of SO3. Now this value is how much? 10 to power of minus 4 moles per minute. That means the rate of disappearance of SO2 will be equal to rate of appearance of SO3. So they are asking rate of disappearance of SO2 in grams per minute. I have got my answer in moles per minute. So I should convert this moles per minute back into grams per minute. How you will convert that mole into gram? You will have to multiply this mole by the molecular weight of SO2. So minus of dSO2 by dt, which is nothing but rate of disappearance of SO2, will be equal to how much? 10 to power of minus 4. This is mole. I will do what? Multiply this by molecular weight of SO2. So this will give me 6.4 into 10 to power of minus 3 grams per minute. So what we are doing here, they have given the data in gram, the equation is given in moles. So I should convert this gram into moles. To convert the gram into moles, what I am doing, I am dividing this data, this grams by molecular weight, I will get number of moles. Now I will get my answer in moles per minute. They are asking the answer in grams per minute. So I will have to reconvert the moles into grams by multiplying number of moles by molecular weight of SO2. Okay, is that clear? After doing the questions on rate of reaction, let us now discuss the next topic, which is factors affecting rate of reaction. There are many factors which will affect the rate of reaction. We will discuss 6 of them one by one. So let us begin with the first one, the surface area. Now see, let us take an example. Suppose if I take a solid cube and if I burn it or I ask this solid to go for a reaction. Now what will happen? In this solid block, the particles which are on the surface, they will get the first chance to react. The inner particles will have to wait for their chance to come. They cannot react until and unless the outer particles have reacted. So they will be reacting one by one. But now if I make a powder out of it, or I break this solid piece into small particles, then what will happen? As I break the solid into many small particles, the particles which were earlier inside this block are now exposed. Overall, the effective surface area has increased. Now all these particles will have an equal chance for reaction. Now you tell me one thing, which will go for a faster rate of reaction, this one or this one? Obviously this one, because here all the particles are having the equal chance for reaction. They all can react at a given moment of time, while in this case the particles will react one after the another, and that's why all the explosives mean, their rate of reaction is very high. All the explosives are in powdery form. So if you make a powder out of it, suppose the rate is R2, this is say R1, this R2 will be more than R1 because we have increased the surface area. Okay, now come to temperature. Now as you increase the temperature, the kinetic energy will be increased. We all know that to have a successful reaction, every colliding particle should possess a minimum amount of energy to go for a successful reaction. So if you increase the temperature, kinetic energy of a particle will increase and they will have more chance to go for a successful reaction. Now not only the temperature increases the kinetic energy, it does something else also. Now let's understand that also. Now suppose this is Maxwell's distribution curve. So this is number of particles, hash means number of particles, and this is say energy. At a given temperature, say T1, this is the curve, and suppose this is the bare amount of energy which is required to go for a successful reaction. Now if I increase the temperature T2 is more than T1. Now the graph will be something like that. This will be for T2. Now if you look at this graph, in the first case when the temperature is T1, these are the number of particles which will possess this bare amount of energy. That means only these number of particles can go for a successful reaction. But in the case of T2, where T2 is more than T1, now these are the number of particles which qualify to go for a successful reaction. So not only temperature increases the kinetic energy, it also increases the number of particles which will have the bare minimum amount of energy which is required to go for a successful reaction. So if I ask you that at T1 and at T2, this is R1, this is R2, which will be more? I know that temperature T2 is more than T1, so rate will also be more for T2. That means we can increase the rate by increasing temperature. Now let us come to concentration term. Now let us take an example. Suppose we are having some particles, and in the second case I am having in the same container many particles, more number of particles. So we all know that to have a successful reaction, the particles should collide. More is the frequency of collision, more is the rate of reaction. Here the number of particles are very less, so their probability of colliding will also be less. Less is the probability of colliding, lesser will be the rate of reaction. Here more particles are there, they will collide frequently. More is the frequency of collision, more will be the rate of reaction. So suppose this is R2, this is say R1, R2 will be more than R1. Okay. Now let's comes to catalyst. This is very important. Now catalyst does what? You must have heard of a word called energy of activation or activation energy. So catalyst increases the rate of reaction by decreasing the energy of activation. If I draw a curve, Maxwell's distribution curve again, number of particles, and suppose this is the curve. Now this is the energy of activation or energy required without catalyst. Now this is the energy required to qualify for a successful reaction with the help of catalyst. Now you can see that in an uncatalyzed reaction, these are the number of particles which will qualify for the successful reaction, and in case of catalyst, these are the number of particles which can qualify for the successful reaction. So what happens? Catalyst lowers the energy of activation. So with catalyst, I am saying the energy of activation, suppose say E2, and E1 is energy of activation without catalyst. So E2 is less than E1. That means R2 will also be more than R1. Lesser the energy of activation required, more is the rate. So catalyst fastens the reaction by decreasing the energy of activation. Now come to nature of reactants. Say for example, I will take a case of combustion reaction, like say twice NO plus O2 will give you twice NO2. See, this reaction is fast. Twice CO, carbon monoxide, plus O2 will give you twice CO2. This is a slow reaction. Both are combustion reaction, but the first one is fast, second one is slow. Why? The reason is that NO, nitrous oxide, is basically what? This is a 15 electron species, and 15 electron species are having a bond order of 2.5, while CO is a 14 electron species. All the 14 electron species are having a bond order of 3. So bond order of 3 will be tougher to break as compared to the bond order of 2.5. That's why this reaction is slow. So rate of reaction also depends on the nature of reactant. If a reactant is reactive enough, it will react faster. If the bonds in the reactant are very strong, they will be very hard to break and the reaction will be slow automatically. Now sunlight. This factor is important in case of photochemical reaction. Say for example, we have got a reaction H2 plus Cl2 in presence of UV light. This will give you twice HCl, and that too with explosion, very fast. And if you go for this reaction in dark, this reaction might not happen, or even if it occurs, the rate will be very slow. So here the sunlight is enabling this reactions to occur at a faster rate. So these are the factors which are going to affect a rate of reaction. I hope this is clear to all of you. Okay, now let's come to our next topic called rate law. What is rate law? See, for any given reaction, rate law is a mathematical form of that reaction that provides you a hint how the rate will change on changing concentration and other terms. So let's look over here. This is a given reaction. Rate law says that rate will be equal to rate constant, concentration of A to the power of m, concentration of B to the power of n. Now this is a mathematical form where m and n, they are the order of reaction with respect to A and B respectively. Okay. Now in this definition, concentration is straight away given the priority. So what we are trying to do? We are trying to measure the change in the rate when we change concentration while keeping all other factors constant. So other factors, they are kept constant, and that constant is called rate constant. So I can say that rate constant depends on all other factors like catalyst, temperature, surface area, etc., except concentration. So if I change temperature, in this rate law, that change should be reflected, and that change will be reflected in the value of K. If I change surface area, again the value of K will change. So rate law suggests you that if I change concentration, how the rate will change by keeping other things as constant. All those things becomes constant, and that constant is called rate constant. You're getting me not? Okay. Doing rate law, we came across a term called order. What is order basically, or what is the importance of order? Now order signifies how sensitive a given reaction is with respect to a given reactant. What I am saying is that a reaction may be highly sensitive towards a reactant, or it might be insignificant from the point of view of a reactant. So let's understand few points with respect to order. It is determined experimentally from rate law. That means you have to go into the laboratory and perform experiments and then come up with the data. From that data, you will have to find out the order of a reaction. Just by looking at the stoichiometry of the equation, you cannot find out a rate law by confirmation until and unless it is an elementary reaction. For example, we have a equation. Rate law will be K into A, that is the concentration of A to the power of m, and concentration of B to the power of n. Now this m and n may or may not be equal to the stoichiometric coefficient. We cannot say with confirmation. We can say that only with confirmation for elementary reaction, where the orders will be equal to the stoichiometric coefficient. Otherwise, in general, the order values are not equivalent to the stoichiometric coefficients. Now the value of order can be negative, positive integer, it can be 0, it can be fraction, I mean it can be anything. Now if a reactant is an excess, its order can be taken as 0. What is the meaning of this? Say for example, I am having an enzyme and there are number of particles, thousands of particles, but we have a restriction that at one time only one particle can react. So whether I am having 100 particles or I am having 1000 particles, it makes no difference from the point of view of rate of reaction. One particle will react at one time, so others will have to wait. So I can say that this rate of reaction is independent of how many particles I am having here, maybe 10, maybe 20, maybe 50, but rate will depend only on one particle at a time. Okay. So let us take an example. For example, I have a rate law which says R is equal to K, A to the power of 0, B to the power of 1. What is the meaning of this? This rate law tells me that this rate is independent of concentration of A. That is why I am saying that it is having a 0 order with respect to A. Now with respect to B, if I double the concentration of B, the rate will also be doubled. Now let us come to this question. It says R is equal to K, A to the power of minus 1 and B to the power of 2. Now tell me what is the order with respect to A? The order with respect to A will be minus 1. From this equation we can say that. Similarly, order with respect to will be 2. What is the overall order? To get the overall order, please add both the orders with respect to A and B individually. Minus 1 plus 2 will be 1. So overall order is 1. I hope this is clear. Okay. So after doing order, let us come to our next topic called molecularity. So while order was experimentally determined thing, molecularity is in contrast a theoretical thing. That means we can design a mechanism, and from that mechanism we can come across what is the molecularity. So what is molecularity? It is the number of atoms, molecules or particles participating in a given reaction, okay, at a given time. Now see that molecularity is defined for elementary reaction. Remember that you cannot define molecularity for an complex reaction as such. You have to break down the complex reaction into elementary reaction and then find out the molecularity of those elementary reaction. Second point, the value of molecularity can be either 1, 2 or 3. 3 is a very rare value. The reason being, it is very difficult for 3 molecules or more than 3 molecules to come together in a right orientation to form a product. Now, the value of molecularity cannot be negative. Why? Because we cannot think of negative molecules, like I can never say that I have got minus 5 molecules of water. Similarly, I cannot say, or it is useless to say that I have 0 molecules of water reacting. Again, there is nothing like fractional molecule. Either we have got 1 molecule of water or 2 molecules of water, but we cannot say I have got a half molecule of water. So the value of molecularity cannot be fractional also. Now see, let us say we are having some elementary reaction, A giving you products. So how many particles are participating in this reaction? Only 1. So molecularity will be 1. A plus B, 2 particles. So molecularity will be 2. A plus 2B, 1 and 2, 3 particles. So molecularity will be 3. Remember that this is a theoretical concept as compared to the order, which is a practical concept. Okay, I hope it is clear. So now let us come to a very important point, and that is rate constant. See student, in examination sometimes they do not give you the exact information or direct information of order of reaction. That order of reaction you have to infer from the units of rate constant. So I'll suggest you, while doing questions of chemical kinetics, you should look at the units of rate constant very carefully, because that will give you a very good hint at the order of reaction. Say for example, the 0 order reaction, the unit of rate constant will be moles per liter per second, which is also the unit of rate of reaction. Now for first order reaction, this is very, very important. The unit is per second or per minute or per hour. Okay, this is important because first order reactions are predominantly in our course. Okay, now for nth order reaction, the unit is mole 1 minus n liter to the power of n minus 1 and second inverse. So you can put the value of n depending on which of the order they are asking. So what is the significance of what we have learned right now will be showcased from this question. So this is a question. They have given a reaction and they have given the value of K 3 into 10 to the power of minus 4. Rate value is given as 2.4 10 to the power of minus 4 moles per liter per second. They are asking at this point when the rate is 2.4 into 10 to the power of minus 4 moles per liter per second, what will be the concentration of N2O5? Now see, rate can be written as K. N2O5 is the only reactant over here raised to the power of m, which is the order of reaction with respect to N2O5, but I do not know the order of reaction. But if I look carefully at the units of K per second is the unit of rate constant for first order reaction. So I can directly now say that this reaction is first order reaction with respect to N2O5. So R will be K N2O5 to the power of 1, or say simply N2O5. Now I know this thing, I know rate also. I can easily find out the concentration of N2O5, that will be rate upon K, and this value rate is given as 2.4 10 to the power of minus 4 upon K is 3 into 10 to the power of minus 4. You solve that, you will get 0.8 moles per liter. So in this question, I saved myself by focusing on the units of rate constant. This is very important. Okay.